Recordings on. Great, so it's week 4. I'm Breon. Do we have any questions for me before we get started with lecture and all that?
For your grading,
Mhm.
the grades that you receive from people supposed to populate in the grades right now, or do you have to? I don't see it.
I have not verified all the grades yet,
Okay.
but I would say 95% of the time they are the ones that people give you.
Okay.
Any other questions? Yes, in the back. In short, the answer is yes. I'm not sure. I had a question earlier about that. I don't know what's going on there. Let me look into it. This is my first time hearing of it today. Cool. Sorry about that. I figured it just was the same as it was last time I taught this class. No, just sent them to you. Okay, do we have any other questions? Okay, let's get started. We're talking about data structures today. And I want to apologize because this is probably the driest lecture because we're talking about just nuts and bolts and under the hood, very nerdy things. So please stop me if I'm saying too many nerdy things in a row. And I hope you're caffeinated. So today we're talking about data types. So far we've been using data frames to make visuals, manipulate and summarize data. And this has taken us pretty far. I feel like we have earned our stripes a little bit and what we can do when someone asks if you know how to do things in R, you can say well, yeah, I can make some okay plots with the Swiss data set, and I can make some pretty cool plots with the, what was the second one? The Gapminder data set with all the countries and things. And I can do some cool joins with the NYC flights data. I feel like those are some legitimate skills. This week, we're going to be getting into sort of the weeds of programming, some of the things that we've been doing so far. And I've just been saying maybe don't worry about it so much. We're going to worry about it this week. So we're going to be talking about all of the non-data frame things we typically use. Well, some of the main ones we typically use, and different types of data in R today. So up until now, we've been using this data frame thing, and we've maybe come to realize that data frames are just like a stack of vectors, that a column is just a vector, and we just have however many columns. In that regard, a data frame is really a list of vectors where each vector is a column of the same length. Okay, so in our data sets, columns are always of the same length, even if they're filled with NAs or something. But data frames are not the only object we want to have in R. Something like a linear regression output. We need to learn about vectors and matrices and lists to do all of the additional things we typically can't express in dplyr syntax, or if we were going to use dplyr syntax for them, it's way too much work and maybe not worth your time. So we're going to start with vectors. In R, we call a set of values of the same type a vector. We can create vectors using the C, lowercase c function, C being for combine or concatenate. For instance, here we have this vector of 4 elements, the numbers 1, 3, 7, and -0.5. Vectors have only one dimension, and that's their length. we can use the length function to check how many elements are in our vector. So here we have the elements 1, 3, 7, -5, and the length of 4. All elements of a vector are of the same type, and this is always true. If they are not of the same type, you have something else. If you mix character and numeric data, the resulting vector will be a character. And this is because it's trying to save as much information as it can. So if we had, for instance, a vector that had the number 1 and the word one, O-N-E, it would default to everything being a character, and you would no longer be able to do math with it, for instance. So to do math, vectors do things element-wise. So when you're doing arithmetic operations on vectors, R handles them element-wise. So for instance, if we have this vector with the elements 1, 2, 3, and we add it to a different vector with the elements 4, 5, 6, it will add them element-wise, i.e. 1 plus 4 for this first element of our resulting vector, 2 plus 5 for the second, 7, and 3 plus 6 for our last element, 9. Vectors will also do element-wise math if you only have one operation to do. For instance, if we have this vector with the elements 1, 2, 3, and 4, and we take it to the third power, it will recycle this operation across each of the elements. So 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, and 4 to the third is 64. And some common operations we might want to do like this would be multiplying all of the elements in our vector by some scalar, dividing them, exponentiating them, and taking the natural log of them. If we work with vectors of different lengths, R will recycle the shorter one by repeating it to make it match up with the longer one. I'm going to say that again. R will recycle the shorter one by repeating it to match the longer one. For instance, here we have a vector with the elements 0.5 and 3, and we're multiplying it by a vector with the elements 1, 2, 3, and 4. And what will happen is the first vector, the shorter one, will just get repeated for however long our second vector is. So here we have 0.5 times 1, then 3 times 2 for 0.5 and 6. And then it just repeats the shorter one. So we have 0.5 times 3 for 1.5 and 3 times 4 for 12. Note that this is an equivalent syntax as this one, as if we had had a vector that was length 4 with the elements 0.53, 0.53. A special case of recycling involves arithmetic with scalars. That is just a single number or a vector of length 1. These are going to be recycled to make, they're recycled to be the length of the longer vector. For instance, we can do 3 times this vector with -1, 0, 1, and 2, and add 1 to that. And if you note, R will obey order of operations for any sort of arithmetic that you might want to do. You can also add in your parentheses wherever you'd like in order to control the order of operations manually. Do we have any questions so far? Okay. I do have an important warning about recycling. Recycling doesn't work so well with vectors of incommensurate lengths. Okay, so if you have one vector that's length 4 and another that's length 3, R will send you this warning, and it's kind of one of the nicer warnings that it'll give you for something that you're doing in base R. So it'll say longer object length is not a multiple of shorter object length. I'm surprised every time this happens to me because of how clear they're trying to be when a lot of their other messages are so weird. But what it's saying is that this vector length 3 is not going to repeat very easily on this vector length 4. And so we don't know what to do. So try not to let R's recycling behavior catch you by surprise. And if you encounter this error for things that aren't adding two vectors together, I hope that you'll see that it's this kind of problem, that it's some sort of recycling issue that's going on. Some functions operate on an entire vector and return just one number. You'll recall from the homework this week when you tried to summarize something that it would not accept a function that doesn't take all the information in a column and make it one number. So this will be a vector-wise math operation instead of an element-wise math operation, something like the sum function. We sum the vector with element 1, 2, 3, 4, we'll get the answer 10. Or if we take the max of the elements 1, 2, 3, 4, we'll get 4. Some other ones we might want to use are the min, the median, the mean, standard deviation, the variance, that kind of thing. Let's look at an example that uses both of these concepts we've covered so far. Let's say we have some test scores and we wanted to put these on a standardized scale. So we're going to make some z-scores out of these test scores. We're familiar with the function for standardizing. We'll take for each object or for each element of our test scores, we will subtract the mean of the whole data set from them and then divide by the standard deviation of that data set. So it might look like this. We'll create this object X, which is a vector of 12 elements. I can't tell with my eyes right now, that are a bunch of test scores out of 100. Okay. And then in order to create our z-scores, we'll assign to the object z x, which is our vector here, x minus the mean of x divided by the standard deviation of x. And when we round it, we'll see that we'll get the z-scores returned back to us. So let's break down what happened here. For each element in x, so 97 was the first one, we had 97 here, we subtracted the mean of the whole vector and divided by the standard deviation of the whole vector. And this was able to generate a z-score for 97, which would be 1.49. And it will return back to us a vector of the same length for each of the z-scores we'd like to generate. So it has recycled these scalars in two places and done element-wise vector math. If you would like to make z-scores, you do not have to write a little function like this. You can instead just use the scale function that's built into R to create z-scores. Do we have any questions there? Okay, am I losing anybody? Okay. So we can use a few different functions in order to check what kind of vector that we have. We can use class, type of, and structure. All three of these will tell us what kind of vector that we currently have. A few of the common types of vectors are numeric. You see this vector has the elements 1, 10 times 3, 4, and negative 3.14. R is totally happy to just have an inline calculation as one of the elements of your vector, as long as that vector is numeric. While it might not be of terrible use to you today, this is a good thing that R does for you. We can also have integers. And integers are just our whole numbers. And note this colon here is a incremental operator. It will create a vector in sets of 1 from wherever you start. Let me try to find where I would run this. Something like this. So 0:10 will give us a vector that is all of the whole numbers between 0 and 10. We also have character vectors, and these are just strings of text. So things like red, blue, yellow, blue. And factors, which are vectors that have a underlying numeric representation and a front-facing text representation. So when we look at this, we'll see that we have red, blue, yellow, blue, and we know it's a factor because it also reports back to us the levels of blue, red, and yellow. But if we look at this inside of class, it'll tell us it's a factor. We could also say, if we looked at it as a numeric, it has this underlying numeric structure. And it's assigned those numbers alphabetically. So when you don't tell R what the factor numbers are supposed to be, it'll just assign them alphabetically. And the other common type of vector are logical, things that are only responding to us as false or true. Like when we were working with logical expressions in week 2 and for the rest of our lives. So we can generate numeric vectors. Numeric vectors contain only numbers with any number of decimal places. There are shortcuts for generating common kinds of vectors. For instance, there's the sequence function. You write as seq. You can say sequence from -3 to 6 by 1.75, and it will create a vector for you, sequencing for equally spaced numbers between -3 and 6, with 1.75 distance between them. We can also replicate a vector using the rep function. So we can say repeat or replicate this vector with the elements -1, 0, and 1 3 times, and it will simply just print this out 3 times in a row. But we could also say each equals 3 to repeat each element 3 times. So we get -1, -1, -1, 0, 0, 0, 1, 1, 1. Integer vectors are a special case of numeric vectors where all the values are whole numbers. We can produce them using the regular sequence operator. So we could do something like create an object called n, assign it the number 12, and then say 1 to n equally spaced by 1. We can also count down this way by saying n to 4, and it will count down from 12 to 4. Are we tracking there? Still making sense? You can also specify a single integer using a whole number followed by an L. This is kind of an old thing about R. You often are not going to need to specify that something is an integer. You could just put a number 9 there. But in the rare case that you do, the way you say this is an integer number 9 instead of just the number 9, you add an L afterwards. Character vectors store data as text and typically come up when dealing with names, addresses, and ID numbers. For instance, we can make this vector first names and assign it the names Andre, Beth, Carly, and Dan. And the class of this vector would be character. Note you can store numbers as character data as well, but you cannot perform math on them unless you convert them to numeric. So something like this was my fiance's lunch number in high school. If you assign it to the object student number and add the number 10, it'll send you back an error saying this is not a numeric argument being sent to a binary operator. And now this hopefully makes more sense about what they're trying to tell you with this error. A non-numeric thing, a character, has been sent to a binary operator, this operator here, where you want two things on either side, binary. We also can work with our factor variables or our factor vectors. They're categorical data that encode a modest number of levels, like for sex or treatment group or geographic region is often where this will come up for us as social scientists. So here I have created the object sex and assigned it a factor with the elements M, F, F, and M. Character data usually can't go directly into a statistical model. A lot of people will just do that in R, and it will convert it to a factor on its own time. Recall earlier I said it will just assign it a number in alphabetical order. This often happens when people add a character vector to some sort of statistical model. Logical vectors take only true and false values and are typically the product of logical tests. So something like, is X equal to 5? We can make logical vectors by defining binary conditions to check for. For example, we can look at which of the first names, Andre, Beth, Carly, and Dan, have at least 4 letters in it. So we can make this vector called name length and assign it nchar, which is here telling us it's a function that just tells you how many characters are in a string. And we can see that our name length vector has these elements: 5 for Andre, 4 for Beth, 5 for Carly, and 3 for Dan. And now we can use a logical expression to say, is name length greater than or equal to 4? And it will return to us a logical vector saying true, true, true for Andre, Beth, and Carly, and false for Dan. Logical vectors also can behave as numeric if we ask them to. So you can do math with logical vectors because the default is that true is going to equal 1 and false will equal 0. For instance, earlier we showed that name length greater than or equal to 4, we get true, 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 false. We can now take the mean of this vector and it will tell us 0.75. And so what has happened here, it told us the proportion of name lengths that are greater than or equal to 4. So this is often like a really nice spot check when you're doing something in R. Is let's say you have a data set and you want to know, how many countries are Canada. And we could just create a logical expression and take the mean of that if you don't want to get into opening up dplyr and all that. So let's talk about combining logical conditions now that we have our foundation. Suppose we're interested in which names have an even number of letters. So we'll make this object even length. We'll assign to it our name length vector, which was just the characters, the number of characters for each of our 4 names. And then we'll use this modulo operator. This is going to do division and then provide us with the remainder. So we're using the modulo and dividing it by 2. So anything that provides a remainder is going to be an odd number. And anything that doesn't will be an even number. So for each of our name lengths, we'll divide it by 2. And if the remainder of that is equal to 0, it's an even number. And our vector, even length, will have false for Andre, true for Beth, false for Carly, and false for Dan. We can also ask R to tell us whose second letter is A in their name. We can create a vector called second letter A and assign it. And here I'm using this function substring. This is a base R function that allows us to select a number of characters within a string and take out that character. So here we're taking the first names vector, and at the second point in the character string, at the start and stop of that point is that letter A, is what our logical expression is asking us here. And we'll get a vector back that says false for Andre, false for Beth, true for Carly, and true for Dan. Okay, are we still tracking? Okay. Now we can combine those logical operators to return a vector. So we'll use the ampersand here, where both conditions must be true to return a true. So if something in the even length of the names and the second letter is A, it will return true. And here we see that all of them are false, which is to say Andre is an odd length name and the second letter is not A. Beth is an even length name, but the second letter is not A. Carly is an odd name and Dan is an odd name. We can use the OR operator with both of these vectors, and only one condition must be true to return true. So for even length and second letter A, Andre is false, but for the rest, they will satisfy some condition. So Beth is even length, Carly has a second letter A, and Dan has a second letter A. Neat. Do we have any questions there? Okay. We can also use the exclamation point to switch our trues and falses, such that we can say that not meeting these conditions, only Andre will not meet these conditions. Okay. We can subset a vector in a number of ways. Passing a single index or vector of entries to keep is one way that I typically use. Something like, we'll take our first names vector, and then we'll put these square brackets to indicate that we want to subset an item from within our first names vector. And then we can pass to this subset function a vector with the elements 1 and 4, and it will keep just the elements that we asked for. So it'll only return back Andre, the first element, and Dan, the fourth element. We can also pass a single index or vector of entries to drop. So using the same format, we have our first names vector in this subset function using the square brackets. And we can say minus a vector with the elements 1 and 4, and it will return just the second and third elements of that vector, Beth and Carly. You'll note that this is like very similar to our structure of how we were keeping and dropping columns with the select function, where we can select which ones we want to keep. And if we want to get rid of specific ones, we would say like minus some column name. Select is stealing this syntax for the same, to keep the same logic. We can also pass a logical vector where true is going to equal keep and false will equal drop. So we can use that combined set of vectors we were using earlier for our trues and falses and say for the first names vector, subset using this square brackets, and then the even length vector, which is just a bunch of trues and falses, or the second letter A vector, which is just a bunch of trues and falses. And when those conditions are met and show true, it will keep Beth, Carly, and Dan. But we could also say first names with our subset operator here, and that vector of the sexes from before, say not equal to F, and it will return back Andre and Dan. So we can use our logical operators or logical expressions within the subset operator in order to drop or keep things based on the true falses that will return from the logical expression. So let's talk about a few of our subsetting functions. We talked a little bit about our percent in percent before. This lets you avoid typing a lot of logical or statements. Something like first names, percent in percent, a vector with Andre, Carly, and Dan, will return a vector that says true, false, true, true for true Andre, false Beth, true Carly, true Dan. One important function that we might want to pair up with our percent in percent is the which function. This is built into base R, and which will tell us the index of where things are true. So what number element in our vector is the true returned. And so with our pet example here of the first names, saying like first names percent in percent Andre, Carly, and Dan, and wrapping that in a which function will tell us 1, 3, and 4. I think in the pet example, this isn't especially useful, but when you have a very large vector and you're looking for one specific thing, knowing that it's element 428,000, whatever, becomes a lot more useful. Let's talk missing values. Missing values are coded as NA without quotes, just capital N, capital A. So we can make this vector here. Vector with missing is what we're going to name it. We're going to assign it a vector with the elements 1, 2, NA, 4, 5, 6, NA. An important thing to know is that even one NA will poison the well. You will get an NA out of your calculations unless you remove them manually or with some sort of extra argument like na.rm. So missing remove equals true in some functions. So if we wanted to get a mean of our vector with missing, it would just return an NA, telling us that there's an NA somewhere in this vector. But if we say mean vector with missing na.remove equals true, it'll return 3.16, going on as if these elements were not in the vector at all. So you cannot test for missing values by seeing if they're equal to NA. Okay, so we can't say vector with missing equals NA. It will return back an NA for all of those elements. Instead, use the is.na function. So we can say is.na vector with missing, and it will return false for 1 and 2, true for the NA in the third element, false for 4, 5, and 6, and true for the 7th element. So an alternative way we could write our mean from before is to say, take the mean of our vector with missing, subset using these square brackets, is.na our vector with missing. And this would return these falses and trues, or as negated them. So true, true, false, true, 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 false, and take the mean of that to get 3.16 or 3.6. Do we have any questions about that? Okay. When testing logical conditions, NA will produce an NA rather than a true or false. Okay, so something like vector with missing equals 5 will return falses, and NA where NAs occur within our vector, and trues where things are equal to 5. One noteworthy thing, however, is that percent and percent will handle your NAs for you. Okay. So you could say vector with missing percent and percent 5, and it will say false where your NAs are. Okay, so percent and percent is a genius, maybe, but it handles your NAs differently. And so it's really important to know that going into whatever procedures you're going to be doing on R, that you need to have like a principled stance on what you're going to be doing with your missingness, right? Because sometimes you want to do something that's percent and percent, and it just throwing back a false would be really bad for your calculations. Sometimes you would want it to throw back an NA. So I would just say, be aware of how many NAs you have and what they mean for your data, and what that means for what kind of calculations you want to do. Let's talk about infinity and not a number. Sometimes we might get positive or negative infinity, or nan, which means not a number, from our calculations. So let's take a vector with the elements -2, -1, 0, 1, and 2, and divide it by 0. So -2 divided by 0 will be negative infinity. -1 divided by 0 is negative infinity. 0 divided by 0 is not a number. And 1 divided by 0 is infinity, and 2 divided by 0 is infinity. I don't really know the math for that. I didn't take calculus, so I'm sure that's true, but don't ask me questions about that after class. You can check for these using functions like is.finite and is.not a number. So you can say is.finite, this calculation we did earlier, and none of these things are finite. And is not a number will only return true for our 0 divided by 0. As social scientists, I don't think we'll run into infinity hardly ever, but something to know. Like data frames, we can use the head and tail functions to preview vectors. So here I say head letters, and the letters vector is built into R. It is just all of the lowercase English alphabet letters. And there's also just the uppercase English alphabet. There's a few others like state abbreviations and that kind of thing. So I'm going to be using that for this example here. Recall that the head function would return back to us the first 6 rows of our data frames. You could also use it to, you could also specify the amount of rows you wanted it to return back to us. So here, when I say head letters, it just gives us the first 6 letters of the alphabet, but also I could specify 10 and it'll give us the first 10 letters of the alphabet. And tail does the same thing as head, but for the last 6 rows or the last n amount of elements in your vector. So let's say that you're doing some sort of like calculation with your vector. It's often good to check the head and the tail to see if those calculations worked. It's typically the case, even on data frames, that if something worked for the top of your data frame and the bottom, there's probably not something lurking in the middle that didn't work. But something at the top or the bottom should be evidence enough if something worked. We can name our vector entries. We can index vectors by assigning names to the entries. So let's say we create a underscore vector and assign it the numbers 1 through 26, spaced out by 1s. Recall this colon operator. And then we can say names to a vector. So we're assigning to the names all caps the letters vector. And since they're commensurate lengths, it will assign the names. And now if we look at just the first 6 elements of our vector, we'll see that the elements 1 through 6 have names, A, B, C, D, E, and F. And now we can use those names to subset our vector. So now we can say using a underscore vector, and subset operator using this square brackets, a vector with RStudio in it. It will return back the names here to keep. Yes.
Can you distinguish this from like factors? Like how we should think
Sure.
about this different from factors?
Sure. So factors, the front-facing part of it, like yellow, blue, red, is the same thing as the underlying number. This is saying that the number has its own name, and it's not necessarily the front-facing part. So we're just using this to index each of these things. Whereas if we had a factor, then like us asking for blue means we're also asking for 3. But sometimes these are going to not have their own name, and we would be asking for like a chunk of things. Does that make sense?
And then the output, is that, should we read that as like 2 vectors on top of each other almost, or no?
It's one vector where each of the elements has a name.
Okay.
Yeah, this will come back up in week 6 and 7 quite a bit, when we need to run functions on really big data sets and we want to name things really quickly so that we know what to iterate over. Names are really nice for subsetting since they don't depend on your data being in a certain order. So we had the numbers 1 through 26, but since they were named, we could pick out the ones that we wanted without knowing what numbers and where they were within the elements of the vector. You can compare this strategy to the one earlier where I showed taking out just Andre and Dan using just the numbers 1 and 4. Right? I had to know in my vector that they were at elements 1 and 4. But if they have a name, I don't have to know where they are within the vector. Okay. We're going to get on to talking about matrices. I think we should take a break here for 5 minutes, and then we'll get back started.
Brian, quick question from the chat.
Oh my goodness, the chat was popping off. My bad, I didn't know. But
yeah, I just had a question about the like the grades.
I can't really hear you very well because of the way it sounds in here. Do you think you could type it? I'm sorry. All right. I think it's been 5 minutes. I'm sorry, chat, that I missed your chats before. I'm very embarrassed. I don't know what to do to make sure that the chat pops up. Okay. If you say something in the chat and I don't address it whatsoever, turn on your mic and say something. We'll hear it. Okay, let's get started talking about matrices. So matrices extend vectors to 2 dimensions, that is rows and columns. So our vectors only had length. Dimensions have, or dimensions, matrices have rows and columns. We can construct them using the matrix function. Note that the by row argument, which determines whether the data fill the matrix by row or by column. So here we can create a matrix. We're calling it A underscore matrix using the matrix function. We're going to input the first 6 letters of the English alphabet, and it will be the number of rows will be 2, and the number of columns will be 3. And so it'll fill A in the first column, and then B in the first column in the second row, and so on, C in the second column, first row. But if we included the by row equals true argument, it will fill from by rows, so from left to right, instead of top to bottom first. We can also make matrices by binding vectors together with the rbind function, short for row bind, and cbind function, short for column bind. We have here C matrix, which we will assign to it cbind, a vector with elements 1, 2, a vector with elements 3, 4, and a vector with elements 5, 6. And it will, by column, combine each of these things into a matrix. So our 1, 2 vector becomes the first column, our 3, 4 vector becomes the second column, and so on. And then we can make D matrix using our row bind, rbind function, and bind together a vector with 1, 2, 3, and a vector with 4, 5, 6. And it will create this structure. Are we cool with that so far? Great. We can subset matrices using the same methods as vectors, except for now we need to index them by their row and column. Instead of just having the length of our vector and being able to subset whatever number we ask for, we have to subset based on the row and the column. So here we can say A matrix, and using our subset operator, these square brackets, we say row 1, column 2, and we'll return C. And then if we want to get something in row 1, but for multiple columns, we would say A matrix, subset operator 1 for row 1, and then a vector with 2, 3 for columns 2 and 3. So you'll get elements C and E from this matrix here. We can obtain the dimensions of a matrix using the, excuse me, I need some water. We can obtain the dimensions of a matrix using the dim function for dimension. This is a lot like using length on a vector. So we're saying dim a matrix, and it will tell us the number of rows, then the number of columns. Note that using length on a matrix will not give you the number of rows or columns, but rather the number of elements. Okay, so for instance, if we did down here somewhere. Wow. Okay. Now if we say length a matrix, it has 6 elements. It'll tell us how many elements are in our matrix rather than the dimensions. If a matrix ends up having just one row or column after subsetting, by default, R will make it into a vector. You can prevent this behavior by saying drop equals false. For instance, if we say A underscore matrix, and then we don't specify anything here in the rows section, we just say our subset brackets, nothing for rows, comma 1. This will tell the subset function we want all the rows, then column 1, and we want it returned as a vector. Okay. But if we said A underscore matrix, again, nothing here for the rows, so we can get all rows, column 1, and then another comma, and we'll say drop equals false. And that will keep our matrix structure rather than returning a vector like the earlier subsetting did. Okay. Matrices can be numeric, integer, factor, character, or logical, just like vectors. Also like vectors, all elements must be the same data type. For instance, we could say we'll make this bad matrix and assign it C bind the numbers 1 and 2 and the letters 14 and 25, whatever the 14th and 25th letters are, and Y. And when we look at the type of matrix, we get character, despite having given it these integers earlier. We can access dimension names or name them ourselves by using the row names and call names argument functions. So here we say row names bad matrix, and we assign to that Candace and John Kell to create our row names. And then our column names of our bad matrix are going to be champion and MVP. And now when we look at our bad matrix, we'll see that our columns have names, champion and MVP, and our rows also have names, Candace and John Kell. And this is useful to us so that we can subset by those names without having to know what element each of our items are. So now we can take our bad matrix and subset using our square brackets to subset based on the name Candace, with nothing in the columns argument here saying that we want all of the columns, and drop equals false, saying that we want it to maintain the matrix structure. And then we get to say Candace Parker was a champion that year. Was she MVP? No. Okay. Do we have any questions there before we move on to matrix math? Okay. So matrices of the same dimensions can have math performed entry-wise with the usual arithmetic operators. Okay. So let's say we C bind our C matrix and our D matrix so that we can look at what they look like. So our C matrix has 1, 2, 3, 4, then 5, 6 column wise, whereas our D matrix was the one that was row wise 1, 2, 3, 4, 5, 6. Now we can say 3 times our C matrix divided by our D matrix. And because they have the same dimensions, we can do the math entry-wise. So we would say 3 times our C matrix, so 3 times 1 divided by our D matrix divided by 1 is 3, and so on. 3 times 3 is 9 divided by 2 is 4.5, and so on. It would do things entry-wise for each of our 2 matrices. Okay, and I know what you're probably saying to yourself if you've done some matrix math before, like this is not matrix math. I tend not to do this one. This one's the one that will mess up all of your math. We're about to get there. So in order to transpose your matrix, let's say you want to like make an identity matrix or something, you use the lowercase t for transpose function. So here we can say our E matrix, we're going to assign to it the transpose of the C matrix. And so now it has been transposed such that the rows and columns have been switched. To do actual matrix multiplication, like the kind we want to do, you use this %*% operator, and this will do matrix multiplication for you so that you get the proper dimensions of an E matrix times the D matrix, for instance. And that will create our F matrix where the matrix multiplication does the correct aggregation on all that. To invert an invertible square matrix, we use the solve function. So we'll make a G matrix and we'll assign to it the solve of the F matrix. And then if we multiply, Now, if we multiply our F matrix times that G matrix, we'll get an identity matrix, right? Where everything on the diagonal is 1 and everything else is 0. And I know what you're looking at this matrix down here and saying, this is not 0. This is not 1. This is because of floating point imprecision. The off diagonals are very, very close to 0 rather than actually 0. This is how computers handle math because they're not very good at doing fractions, but they're really good at doing decimals. So to them, this number is the same thing as 1. 1.0 with a bunch of trailing zeros and a 4 is the same thing as 1. And it doesn't tend to mess up your calculations in any way, but do note that that's going on under the hood often. Or like this -3 times 10 to the -15 is 0, but sometimes it will look like this. It will not mess up your calculations. Yes.
Sorry, I was lost with solve and the vertical square matrix. Can you explain that again?
Sure. What would you like to know?
I was understanding that solve was flipping the order of the rows, or is that incorrect? I'm not sure what solve does. What's there?
I'm trying to think about how to explain inversion because I don't tend to do it. Like the only reason I would use solve is to if I was fitting my own maximum likelihood, and like I don't tend to do that. So I'm trying to think then what you would use it for. So it creates the other matrix that you have to multiply by your current matrix in order to make the identity matrix.
Okay.
Yeah. Like maybe Adrian Dober is going to be mad at me for saying that incorrectly, but that's how I recall. So about floating point imprecision, be careful testing for equality of numbers after calculations because sometimes that imprecision will create strange results. But I feel like you'll typically know when you're in that situation. For instance, like if you say something like 0.333333 times 3, like it's just going to tell you it's a 1, even though like in your brain you're like that's just 0.99999, you know. To extract the diagonal of the matrix or make a diagonal matrix, usually the identity matrix, you can use the diag function. So let's say that you have like a variance covariance matrix and you just want your coefficients from your model. Here's your diag. I know that this class doesn't assume that you know a lot of statistics, so like I'm telling you, these are some things that you might want to use when you do statistics. But if you don't know what I'm talking about at all, don't worry about it. So we're going to move on to talking about lists, unless we have any other matrix questions. Okay. So what are lists? Lists are objects that can store multiple types of data. That's kind of it. They don't really have rules also. You can just kind of put anything you want into lists. They're wildly flimsy and you can just, I don't know. We'll get into talking about them. So for instance, I'm going to make this list. It's going to be called my list. I'm going to create it using the list function. And the first element of my list is going to be named first thing. And it's going to be a vector with the integers 1 through 5. Okay. The second thing is going to be a matrix with the elements, the integers 8 through 11 with 2 rows. And then the third thing is going to be the entirety of a regression output of distance by speed using the cars data set that we used way back when. Okay, so in my list, I have a vector, a matrix, and a regression output. In order to access list elements, you can use its name or number using double square brackets. Okay, so the double square brackets, this extract operator or subset operator, or you can use a $ followed by its name. For instance, you can say my list double square brackets, so subset the first thing, which was the name of our first element of our list, and it'll give us back this vector with the integers 1 through 5. We can also say my list with the extract operator, the $ of the name first thing, and it will give us the first 5 elements. And we can also say my list double square brackets, the number 1 for the first element of the list to get the same thing. These are all equivalent expressions. Okay, cool here. So why 2 brackets? The reason is if you use single brackets to access list elements, you will receive a list back. So double brackets will give you the actual element as whatever data type it was stored as. So because I used the double brackets before, we were able to get a vector back. But if I use single brackets here, it will say this when I run the structure of it. It will say list of 1 element. It's called first thing. It is an integer with these elements. Whereas if I say structure my list double square brackets for my first element, it'll just return the integer vector with the elements 1 through 5. Okay. Note that you can only select a single element at a time using the double square brackets, because this would have returned multiple objects. And every time I say this, I know somebody's mind gets blown, and it's normally me. And our function can only return 1 object at a time. I know it seems sometimes like it's returning a bunch of stuff, but it can only return 1 object at a time. And the reason is because if it didn't only return 1 object at a time, you wouldn't be able to assign things. I know. It's wild. So there's also this really excellent picture of how the single brackets versus double brackets works. So let's break down what's happening in this picture. So we have this object X, which is a shaker that has inside it packets of pepper. Okay. And if we did only 1 bracket, we would extract the element with just 1 of the packets of pepper, but we would keep the container still. But if we use the double square brackets, we get our packet of pepper. And if we use double square brackets twice, we get the pepper inside of the packet. I look at this picture every time I need to extract things from lists. You don't have to worry about it so much. One thing to note is that you can string together square brackets like this in the case that you have a list that has other lists inside of it. Yes, question.
The second one, the double brackets, like for your vector, like
Mhm.
if you wanted to get 2, could you just specify the second element?
Yes, you could. Mhm. Okay. Subset lists can be of length greater than 1. You can use vector style subsetting to get a sublist of multiple elements. So something like, let's get the length of my list with the elements, using a single bracket here for a vector 1 and 2. And it will extract just the things from my list that are the first 2 elements of it. So something like return me a list that has the first thing and the second thing within my original list. One important thing to note is that regression outputs are themselves a list. Okay, so I know it doesn't seem like it when you run a regression in R, but the only way to store so many different kinds of things like a regression output is as a list within R. So here, we are looking at the structure of the third element of my list, which was that regression of speed and distance using the cars data set. This is just to only display the first 7 elements of in the slide, but we'll see that things like the coefficients are a bunch of named numbers in a vector, whereas I don't know, our residuals are incommensurate lengths with our coefficients. So in order to store all that information, we would have to use a list. You can use names, the function, to get a vector of the list element names. And this allows us to subset without having to know what element of the vector that we're interested in. Right, so like sometimes you want to just get the residuals and the fitted values, so you can make a residuals versus fitted plot or something of that that nature. Sometimes you want just the coefficients. Being able to subset by the names means you don't have to know where they are in the list. Yeah, I'm trying to think. Do we cover everything here sufficiently? I think so. One important thing also is that data frames are lists. Data frames are lists, with the only caveat being that they are equal length vectors. So all of the elements of the lists have the same length, but they do not have to be of the same type. For instance, when you look at the structure of the cars data set, it has all of the trappings of a list and how it comes out in structure. It'll say data frame, but it's in quotes like, yeah, it's a data frame, whatever. It's actually a list. And then it'll also tell you the number of observations, which is always going to be the same length because it's a data frame, and how many variables it is. And then again, this extract operator is telling us what things we can extract by, but also what elements our data frame has. The length of a data frame, you might have noticed before, is not the number of rows it has. It's the number of columns, because the columns are like the elements of a list. In order to look at the length in terms of the rows, you would have to look at the element of the extracted thing within the list. I know. It's wild at the end of it today. You can also treat data frames like a matrix. So if you want, you can say cars with the extract or with the subset operator, just the first row and all of the columns, and it will provide it to you like this in the same format. And you can even say things like drop equals false, or take the first 5 rows and give me the speed column, and I would like it to stay as a matrix, and it would turn out that way. I know, data frames can kind of do anything they want. So I say all that and a lot of today to help motivate why we might want to use dplyr. For instance, here's 2 ways of calculating the same thing. Here is the mean of the education column in the Swiss data set when the rows are above the mean of the education column in the data set. So I'll say it as this is written. Give me the mean of the Swiss data set, subset to all of the rows where the elements of the Swiss data set's education column are greater than the mean of the Swiss data set extraction of the education column, and only return back the education column. And then in dplyr, we would say instead, take the Swiss data set and then filter the education column that's greater than the mean of education, and then summarize the mean is equal to the mean of education. And I find this to be easier to read, although sometimes I think of this as the first way to how to answer a question. So one other thing that I want to get to today is that these things are equivalent and it's okay. And oftentimes what happens is you'll sit down and you'll have a very particular question about your data set, and maybe writing all of this doesn't come to you first, and sometimes this does. And that's okay, because they are equivalent expressions. Oh yeah, and let's talk about tibbles. So tidyverse functions often use a type of data frame called a tibble. You can create them manually with the tibble function. It's like making a data frame using data.frame, or convert existing data frames into tibbles using as_tibble. Tibbles display better than data frames, which is that they truncate output and include column types. And they don't convert strings to factors. Okay, actually, I always forget to take this out of the slide. That no longer happens. That's a R 3.0 thing, but we're way on to R 4.0, so don't mind that I said that sentence. But because the tidyverse has gotten rid of row names, tibbles don't have any. You can convert row names to columns using the row names to column function. For instance, you'll recall in the Swiss data set, we had the names of all the provinces, but they were just the names of rows. They were not their own column. This is bad practice. What you would want to do is say something like, take the Swiss data set and then as_tibble row names equals name. And it would give you the row names here as its own column. And this is way more flexible and useful, and would have been more useful when you were making your plots and things in the first homework. I also want to provide a little bit of an aside for people with statistics training. If you don't really have statistics training, you can just like chill for like 5 minutes. Okay, so you can get the fitted regression coefficients. Recall this my list in the element 3 is output from a regression model. So we can get them by saying something like my list, this third element in double brackets, and then the double brackets coefficients. Because our regression outputs are also lists, we have to double bracket again. And then we can get a particular beta by chaining together all of these double brackets and then a single bracket for this last one. Okay. So when we want to summarize a regression output, we will say like summary our regression object. This will also be a list with more information, which has the side effect of printing some output in the console. So like when we say summary, it'll print all of this other information that sometimes we don't really care for. Like who's still using R squared, am I right? But one thing I want to highlight is that it's given us all this information. And if we wanted, we can use things like the subset operator to get all of that information. So I think one of the strengths of R is that nothing is off limits in terms of what you can take from your objects. So for instance, we could say summary my list and then double brackets to subset the coefficients, and it could give you just the coefficients that you're interested in. And if you wanted to get the specific standard errors, you could get them in the same process by creating like a speed standard error object and assigning to it the summary of your regression object here, and then subsetting the coefficients. And then for the speed row, give me the standard error column. And you could get that particular standard error. And then, yes, question. Why is this in parentheses, or why is this parentheses? So like the one that's wrapping the whole thing, or just the summary? Yeah. Okay, so the reason it's the whole thing, if you'll recall, I think from the second week, is if you do that while you do an assignment, it will print to the console. what gets assigned, and that's how I get it to go on the slide. But since you can extract something like the standard error that you saw in your original summary at the output, using all of these chained together subset operators, you can then construct your own confidence interval. This Q norm is just saying, give me the quantile of a normal distribution. And I'm saying like, give me the bottom 95 and the top 95%, or the top and bottom 5%, or 2.5, whatever, in order to create our standard errors. And then we can name it something like this. And now you can include these values in a markdown document. So you could say something like a 1 mile per hour increase in speed is associated with a backticks R round speed beta 1, feet increase in stopping distance, and then our 95% confidence interval that we've extracted from our original regression output object. And it would look like something like this. A 1 mile per hour increase in speed is associated with 3.9 feet increase in stopping distance, 95% confidence interval, 3.1 and 4.7. This is a very long-winded way to tell you that if you wanted to do like bootstrap your own standard errors or something, or mess with the convex hull of your maximum likelihood optimizer or something like this, you totally can. Instead of having to like be upset that some fit is singular or something in Stata. Okay, so people who don't have a lot of statistics background and don't care about what I just said, you can come back now. We're going to talk a little bit about our homework. One thing I want to point your attention to is a suggested practice that you could do. It's a package called Swirl. It does interactive R tutorials that cover a lot of structure basics in R. So you can say like install that package as Swirl, library Swirl, and then run this function. And then you can choose what program you'd like to run, and it will walk you through some tutorials. And then when you want to be done doing those tutorials, you can just type bye, and you won't have to do Swirl anymore. But it's pretty good. I remember doing Swirl when I was like a first year R user a little while. It's something you might want to check out. Let's talk about your homework. So there's actually 2 choices for the homework this week. The first is less advanced. You fill in a template R markdown file that walks you through creating, accessing, and manipulating R data structures. You enter values in the R markdown document and knit it to check your answers. And you're going to knit after entering each answer. Knit after answering each question. If you get an error, check to see if undoing your last edit solves the problem. Coding an assignment to handle all possible mistakes is really hard. And this assignment, I think, is pretty long, so start early. There is a more advanced homework, which you will walk through doing a linear regression by hand. It's very similar to the other one. You're going to fill in a template R markdown file that walks you through 1, doing a linear regression manually, and 2, comparing it to the built-in LM function. It includes simulating data and creating and modifying data structures. Again, knit after entering each question or answering each question. This assignment does not check your answers as you go like the other one does. But it's also pretty lengthy, so start early. But I also want to show you how to access the homework. So first, it will be here. So you just click on this, it will download. And first thing you can do is knit this homework. Okay. And I'll talk to you a little bit about what's going on here. So for this assignment, you'll practice creating, examining, and combining different data structures in R. This assignment is different from others in that it takes a worksheet format and it has built-in error checking. Each time you complete an answer, if you knit the document, it should check your answer. Do not remove anytime it says null on an answer before you want it checked by the checker. For this reason, you should reknit every time after you answer a question. So in order to complete this homework, you will need to do the following. Number 1, fill in code as needed in the designated locations and code chunks. You'll not need to create a new code chunk or edit chunk options ever for this assignment. Instructions in chunks will be shown as comments, so they're going to be after a hashtag. So remove and replace those comments with your code. Where you're assigning things to objects, replace the null values with your code. See code example 1 as an example. So here it says example 1, create a vector with the numbers 1, 5, 3, 2, 4. So example would be this. And then if you want to answer this question, you would write this. So you have to overwrite this null here with the answer. Okay. So some answers may require multiple lines of code, so add as necessary. Do not modify chunks that are labeled do not edit. These are used to test your code. And it is very fragile. It's not the perfect answer checker. I've tried to conceive of all possible versions of how you might want to answer this and miss, but it's hard to know. The second thing that you'll need to do for this homework is fill in text as block quotes using the greater than. So that's how this example is. So be brief and specific. If you reference a single value or a less than 10 element vector, use inline R code. If the answer can be clearly and accurately answered without referencing any values, you can and probably should do so. When I bold a word in a question, take it to mean I want you to reference a value or values. Do not directly reference matrices, lists, or data frames in text. Don't display them. They can get really big for this assignment. You should not need to include any code chunks in this section, but you can if needed. Okay. What did you say about not removing the null? Don't remove the null if you don't want that question checked. So if you want a question checked, remove the null and write an answer. Okay. So question. Let's find out. Okay, so this chunk here says do not edit, so I'm not even looking at this. And I'm going to scroll on down here to this first question. So it says, yeah, so use sequence to create a vector of 10 numbers evenly spaced from 0 to 15. So let's say I say sequence 1 to 16. Okay, and now I'll knit. And now it says, oh no, check your code for vecnum. Wrong length or dimensions, wrong object class. You seem to have an incorrect or misplaced value somewhere. And it will do this for this how did you do section for all of the questions for this homework. Another thing to note about this homework is now we're in the part of the quarter where during lab, I will walk through the homework step by step. And should you not have time that week or would just like to have your answers answered, I will also be recording that and you can just copy what I'm doing and turn it in and you'll get a 3. I'm also expecting that the comments that you leave on peer reviews will be a little bit less fun, and because you might just have copied what I walked through. So no worries if your comments are very brief or just like, I just like this one thing, 3 out of 3, you know, something like that. So do you have any questions? Okay, great. Well, that's it, everybody. Y'all have a good one.
Are you gonna walk through both assignments? Or you think
Oh
you're
yeah,
just
for
done?
this week, I am not walking through both assignments. Yeah, I'm gonna walk through just the less advanced one. I reckon that people who approach the more advanced one will have a very particular set of questions for me, and we can just deal with that on Slack.